Look at any modern machine, a spacecraft, autonomous vehicle, or next-generation jet engine. They are massive, interconnected webs of hardware, software, data, and human interfaces. This technical evolution has reached a point where a single system now encompasses millions of distinct components, creating a level of complexity that is difficult for any one human to fully visualize. Because these disciplines must fuse together perfectly, the traditional methods we've relied on to design and manage them are reaching their technical breaking point. For decades, system engineering has relied on a document-centric approach. Requirements, architecture designs, and interface definitions were recorded in static text files and isolated blueprints. In this environment, a single design change forces engineers to manually track down and update hundreds of disconnected documents across different departments to ensure they still match the physical reality. This manual process leads directly to data fragmentation. Information becomes inconsistent across teams, making it difficult to maintain a shareable, accurate understanding of the entire system architecture. Relying on static paperwork to build dynamic, interconnected systems creates a technical vulnerability, increasing the risk of project delays and hidden design errors. Many organizations attempt to solve this by utilizing 3D CAD tools or domain-specific aerodynamic simulators. This illustrates engineering with models. These tools optimize specific domains perfectly, but remain isolated clusters, disconnected from the whole machine. Effective integration requires a multi-view architecture, where every node, from the macro system to the individual component, is dynamically bridged together. Moving past these fragmented tools requires a framework where the model itself drives the engineering processes, activities, and tasks. The ISO 24641 standard provides this framework, defining model-based systems and software engineering, or MBSSE. Under this standard, the digital model serves as the primary evolving source of knowledge for the entire organization. This diagram shows the MBSSE reference model, which organizes engineering activities into a coordinated engine made up of 4 interacting process groups. The Plan group establishes the governance and rules for the models. The Perform group then identifies the specific technical problems and system concerns that need to be addressed in the current development phase. These concerns are fed into the Build group to be translated into testable models. Meanwhile, the Support group provides the back-end infrastructure for configuration control and technical quality, keeping the entire loop running smoothly. This dynamic architecture replaces static paperwork with a digital ecosystem, allowing engineers to connect millions of moving parts and analyze their interactions instantly. But how does this engine actually generate value? This pyramid diagram shows the mechanism of transformation: data, information, knowledge, and wisdom. During the build phase, engineers start with raw isolated numbers and text, data. As these points are brought into the model and structurally linked, they are organized into visual, understandable information. Next, this information is rigorously tested against semantic rules to ensure it covers all required system concerns. Once verified, it becomes trustworthy, reusable knowledge. By running virtual simulations on this knowledge, engineers can predict behavior and identify potential failures before they happen. This predictive capability is wisdom. MBSSE actively processes data up this pyramid, catching structural errors and optimizing designs long before any physical components are manufactured. The most practical outcome of this transition is dynamic correlation. If a software engineer modifies a line of code, the unified model calculates how that change impacts the physical hardware design, the power draw, and the thermal constraints across the entire project. This ensures comprehensive traceability. Every element, from the customer's initial requirement to the final test result, is perfectly aligned and accounted for in a single digital environment. Adopting ISO 24641 integrates technical tasks with a centralized governance model, ensuring every design decision is backed by the latest system data rather than outdated documents. This creates a digital thread, an unbroken line of information that remains accurate through the entire lifespan of a product. As human-made systems grow more complex, this interconnected framework provides organizations with the high-fidelity oversight needed to maintain their competitive edge in a demanding technical landscape.